This is my Physics 2212 lab on circuits. The goal of this lab is to predict the behavior of circuits containing resistors in series and in parallel. I examine the behavior of ohmic resistors and capacitors and use multimeters to measure experimental values of conventional current and potential differences. Lastly, I compare experimental values to calculated values. Below are a preview of the results from this lab. For the main concepts, we use the node rule and loop rule. The node rule states that the sum of currents flowing into that node is equal to the sum of currents flowing out of that node, which follows the conservation of charge. The loop rule states that the difference in potential for a round-trip path around the circuit equals 0. From this, it is important to note that the loop rule can be used to calculate the current and the potential difference at different areas of a circuit. Electrical resistance measures how much an object slows down the current, and one constant can be defined by Ohm's law, which states that the resistance is equal to the potential difference divided by the current when resistors are in parallel. Their equivalent resistance is the sum of the inverse of the resistances of the resistors. When resistors are in series, the equivalent resistance is the sum of resistances. Capacitance is a measure of charge that can be stored in the capacitor for each unit of potential difference. Capacitance is equal to the magnitude of the charge on one capacitor divided by the potential difference, which is equivalent to the area and the vacuum permittivity divided by the separation distance. Here are some visual models for the circuits that were created in this lab. The system is a device measuring the current or potential difference. The surroundings is a circuit being measured. So first I created a simple circuit with parameters shown. The ammeter then measured the current flowing through the circuit. It's important to note that the predicted current and measured current are nearly identical when the ammeter is reversed and the measured current is negative as the current enters the ammeter through the other end. Then an open circuit was created by using the simple circuit, but one ammeter is replaced with a voltmeter. The result is measured with a potential difference of 3 volts from their batteries. The current is 0 amps because a voltmeter has a high internal resistance, so flow of the charges is essentially 0. Now the voltmeter is replaced with wire, and the potential difference at different points in the circuit were measured. Importantly, the potential differences satisfy the loop rule, as the sum of the potential differences equals 0 volts. The graphs show the sum equating to 0 volts. Now the same circuit is reconstructed such that an ammeter is parallel to the 100 ohm resistor. The resulting current is greater than the current from the original circuit because the resulting junction allows for more current to bypass the resistor, allowing for the overall current to increase. Next, I calculate the resistance of the resistors, ammeter, and wire based on the experimental values. This was calculated using Ohm's law, which is shown here. The results of the resistance according to their components are shown below. An RC circuit was constructed with the components shown on the slide. Then, the time to charge the capacitor and the time to discharge the capacitor was measured for each resistor. The time to charge nearly equates the time to discharge the capacitor. Between the two capacitors, the 20 ohm resistor leads to a near doubling of the time to charge and discharge relative to the 10 ohm resistor. An RC circuit with the components shown on the slide was constructed. The circuit was then closed to allow the capacitor to charge. Then the battery was moved and the circuit was closed again to allow the capacitor to discharge at 1 second intervals up to 20 seconds. The potential difference of the capacitor was measured. Finally, plot the natural log of potential difference divided by the initial potential difference was taken over the time. The plot with a linear slope, which is then used to calculate the time constant RC of the RC circuit. This time constant equals 5.94 seconds. Note that the calculated resistance values are greater than the actual resistance values due to the lack of precision and the ammeter in the simulation. In addition, there are other sources of error which may include rounding errors during calculations, timing errors when determining the charge and discharge times for the RC circuit. If an actual ammeter was used instead of the ideal simulated ammeter, the ammeter would read a slightly lower current value due to the fact that a real ammeter has a small non-zero resistance. Next, if I were to use a real battery to charge a real capacitor with no resistor, then the real circuit would not charge up instantaneously because of the resistance due to the wires and in the capacitor, which impedes the current, leading to more time for charges to flow through and therefore build up. Thank you.